Hello. Great. We're ready to go. All right. Great to be here. Thank you for inviting me, Erica. I'm Adrian. I'm one of the co-founders of Anoma. And today I want to give you sort of a brief glimpse of Anoma and what we are doing with Anoma, which is a unified architecture for full-stack decentralized applications. I'll start with a sort of brief historic recap here of where we started, where we are today, and I think where we're going to go in the future. The very first thing that we got was, and by the way, so like a lot of other people historically have used different delineations for how these, like how you think of generations, evolutions of blockchains, and I think what I'm presenting today is very different from this, but I think it's somewhat more sensical. So really the first generation of blockchains was scriptable settlement, and this is what we got with Bitcoin in 2008. Bitcoin was massively innovative at the time, and it was great at building things like cryptocurrencies. Interesting enough, people started to build applications like colored coins, Namecoin, and a long tail of Bitcoin forks on top of Bitcoin. The important thing to remember though is that they were incredibly clunky. Like colored coins weren't easy to use on Bitcoin. Namecoin wasn't easy to use. Namecoin even required a fork of the original Bitcoin client in order to make it work, right? But this is what scriptable settlement gave us. And to me, this is really the first generation of blockchains. Then we got Ethereum, and Ethereum sort of ushered in the second generation of programmable settlement. And Vitalik actually talks about this in the original Ethereum white paper that like one of the motivations for Ethereum was that colored coins on Bitcoin was incredibly clunky. And we needed something that was more expressive, more programmable than simple Bitcoin script. So we moved from colored coins to ERC20s, we moved from Namecoin to ENS. But the really important thing to remember is that when Ethereum was designed in 2014, we thought of a couple of applications that you can sort of bring over and make more efficient going from Bitcoin to Ethereum, but there was a host of other applications that we sort of discovered later on are actually incredibly powerful and can be built only on programmable settlement. These include things like DAOs, like NFTs, soul-bound tokens, what Vitalik just spoke about, right? So there was this host of new kinds of applications that were enabled by programmable settlement. And you see this nowadays, right? That there's a ton of more applications just outside of ERC20s. There is now we have modern applications like DEXs, AMMs, NFT marketplaces. But I would argue that they currently have similar downsides on Ethereum or on essentially programmable settlement layers than we had on Bitcoin with colored coins in the past, right? They're generally still clunky to use. They generally still require at least one centralized Web 2 component, which, for example, in the case of OpenSea is users, Alex mentioned intents, right? Like users don't send transactions on Ethereum when they interact with OpenSea. No, they sign a message and they send it to a centralized Web 2 server run by the OpenSea team that then does some compute and then ends up settling some output of that compute on Ethereum. This is the same for 0x. This is the same for CowSwap. This is the same for Optimism and Starknet too. It's always the same pattern. People don't directly interact with these systems because they require interactivity. How do you get interactivity in the current model? Well, you send stuff to a Web 2 server that does some compute and then settles after you have done the interactive step something on a programmable settlement layer. And I mean, historically people keep talking about like generation 3, generation 4, and like any upgrade in a consensus mechanism is a new generation of blockchain. And I would actually argue that in terms of what they fundamentally bring to developers and what kind of applications we can build on these systems, they're really, really similar to Ethereum. I call them second generation plus plus. So we've made some advances in, for example, proof of stake, Sybil resistance. We moved from proof of work to proof of stake, and that's now working really well. We also made tremendous advances in consensus mechanisms, like we have Tendermint now, we have Avalanche, we hopefully eventually get ETH2 single slot finality, right? But it's still fundamentally the same model. It's programmable settlement. It's the chain does nothing but settle some state transition. Yeah, so in the end, it's still programmable settlement. The important thing to remember, though, is that settlement is not sufficient. Settlement is sufficient if the parties already know who they are, what they want, and with whom to coordinate. This is generally not true for most interesting things. Like if you think you want to sell an asset, like you want to sell some ETH for Bitcoin, you need interactivity to discover a counterparty that has the inverse. If you want to sell an NFT, you need a counterparty. So pretty much everything that's interesting requires some amount of counterparty discovery. Like the only thing that doesn't actually require interactivity or counterparty discovery is if I want to send money to myself. Like if I want to send money to myself, I have all the state that I need. I know my addresses, and for example, I can use as a result like something like Tornado Cash on Ethereum. That actually doesn't require counterparty discovery, but it's a minuscule part of sort of what I would consider interesting applications at the moment. Yeah, so many applications actually need this kind of counterparty discovery service because it is really difficult to have a decentralized way of like, oh, I want to trade Bitcoin for ETH. Oh, Bob in San Francisco has the inverse of this transaction and is willing to coordinate with me. So you see this everywhere. You see this in marketplaces, like OpenSea is a great example here. You see this quadratic public goods funding with Gitcoin. You have project donors and funders that all need to discover each other. You see this also in DAOs. Also, you see this in rollups. Like rollups also need counterparty discovery because this is exactly what a rollup server does. Like this is what the optimism server does. It aggregates a bunch of people's intents, does some compute, so it like does the counterparty discovery and solving for this system, and then settles it on some underlying base layer, at the moment Ethereum. So how do we currently deal with counterparty discovery? Well, we have AMMs, and I would say AMMs are sort of the best answer we have to counterparty discovery if we live in a programmable settlement world, right? Like if the thing that you have available is programmable settlement, an AMM is probably the best thing you can do to enable decentralized counterparty discovery, because you just treat the Ethereum consensus state as this is the main counterparty discovery point, and everyone talks to this and everyone sees the state updates. The problem is this is very expensive because everything has to be now globally ordered, and it's incredibly silly because you don't need a total global order to be established to say, oh, I want to trade some ETH for Bitcoin. This is mostly that like it's a side effect of just being stuck in this programmable settlement world. On-chain order books kind of do exactly the same thing, where like the easy answer is always you just dump everything on-chain and establish a total global order over the transactions or the intents and then have the system figured out. But it's really expensive. So the other very common approach nowadays is single operator databases that just act as centralization points. So OpenSea does this with a centralized OpenSea server run by the company. 0x relayers do this. Flashbots, interestingly enough, it's exactly the same pattern. In Flashbots, people sign a message, they send it to a centralized Flashbot server. They call this the MEV relayer. That does some compute and then settles on a chain, right? Yeah, rollup sequencers do this. So these are always trusted parties. In the best case, they can't steal your money. In the worst case, they are effectively a centralized exchange that can run away with all your funds. This is why we've designed systems like fraud proofs and so on in order to like reduce the trust assumptions on these central parties. But in all cases, these trusted single operator databases can censor you, as in they can prevent you from interacting with the system because they have a single IP address that can just block your submissions. And now there are some other approaches like app-specific sovereign chains. DYDX is trying this out right now. There are a lot of other downsides because now all of a sudden you have to launch your own blockchain. It's a lot of dev work. You lose full composability across the ecosystem because all of a sudden, to be fair, you already don't have this on current programmable settlement architectures, where like specific intents are siloed in their little application. I can't build a new application that reasons over, let's say, the OpenSea and the 0x intents at the same time. So today I'm going to present Anoma, which is, it's an architecture. This is sort of an important thing to understand. It's an architecture with many different deployment models. You can deploy, and I'll speak more in depth about this in a bit, but you can deploy Anoma as an L1. Many people can deploy Anoma as many L1s. Like if a city wants to take Anoma, deploy as an L1 that works too. You can deploy this as an L1.5 or as an L2. Yeah, so Anoma is a unified architecture for full stack decentralized applications. What does this mean more in depth? Well, the really long but all-encompassing tagline is that it's an intent-centric, privacy-preserving protocol for decentralized counterparty discovery, solving, and atomic multi-chain settlement. I'll go through the first part of the sentence, not so much atomic multi-chain settlement. There are other talks. I don't have like 2 hours to explain atomic multi-chain settlement today. So what are the key design principles? Well, one, it's intent-centricity. And 2, it's homogeneous architectures and heterogeneous security models. And we've already spoken a little bit about what does it mean for something to be intent-centric. It's the idea that users express what they want and not how to get this. This is also honestly like the mental model that I think everyone has when they interact with a blockchain. But what you currently do effectively in whether this is the EVM or the Near VM or the Solana VM, it's always you don't actually express what you want. You authorize an execution trace. Like when you send a transaction on these systems, you authorize not a specific future result. You authorize there are these opcodes, and these opcodes can do arbitrary compute. As a result, this means as a user, you have to audit, honestly, every single opcode that you sign over, because otherwise you can have proxy contracts that steal your money. Because they can do arbitrary things, because as a user, you never defined what you wanted, you just defined on how to get it. This is also something that I think my parents will never be able to understand in terms of the security model that they have when interacting with blockchains. Like when someone taps their card in a store, they don't think I'm authorizing all API calls between all Visa servers, and they may do arbitrary things, and afterwards I should check whether they cheated me. Like the mental model is you tap your card and you're authorizing a specific state transition. Like you're authorizing that some money is debited from your account. So intents are binding programmatic commitments to state preferences. Once you think more about intent-centricity and how you design underlying architectures, a really nice other feature is that it falls out that you can have a P2P intent gossip network that doesn't have to be globally consistent. As in, everyone in this room can have a different view of the current available intents in the world. So as a result, you can have like 100 billion intents floating around because they're not consensus critical. We don't need a globally consistent view of them. And different people can opt in to receive different intents, right? Because maybe I only care about the OpenSea intents because I am into NFTs and I want to see all the NFT trades. So I can only subscribe to the open. Is that a fire alarm? Okay, good. Right. So now you have an intent gossip network, right? You have 100 billion intents floating around. They're not settled actually. Like they're just like what individual people want. How do you actually end up combining these intents and creating transactions out of this? This is where solvers come in. They exist pretty much right now. Like an OpenSea server is already a solver for OpenSea. The optimism sequencer is already a solver just for optimism specifically. A Starknet prover is a solver just for the Starknet specific intents. But with Anoma, you can have a generalized intent. And then you can have solvers that go, these 15 things are combinable. Maybe there are some fungible token trading, right? Because you can do things like, user A wants to do ETH for Bitcoin, user B wants to do Bitcoin for Near, and user C wants to do Near for ETH, completing the cycle. So you can settle an arbitrary number of intents in the same transaction. So solvers, they will most likely specialize in some specific intents. Building generalized solvers is very hard. This is probably an NP hard problem. So if someone can solve this, you will make a fuck ton of money because you can sort of solve over an arbitrary state transition. Practically speaking, different solvers can specialize for different kinds of intents. So for example, you can specialize for fungible token trading, you can specialize for NFT trading, you can specialize for like lunch date setups, because the important thing to remember about intents is that they're fully programmatic. As an intent is just code that you're trading with other people. It is not specific to actually like what you think of a financial transaction or trade. You can say that you can use the intent system to express that you want to meet someone that is into board games at a cafe in Seoul on like Sunday at 5 p.m. It's just whatever you can write in WASM, you can express as an intent. There are no restrictions here. Yes, and this leads to a nice feature that intents are fully composable. You can reason as a solver over the OpenSea intents, the optimism intents, and like a normal trading intent at the same time, and figure out which ones are combinable there. Then solvers create transactions, and transactions are then settled on a settlement layer. And here it actually doesn't matter which settlement layer. This is why I mean that you can deploy an architecture like Anoma to Ethereum as an L2, where Ethereum just ends up being the settlement layer. This kind of intent-centric design is what everyone is discovering at the moment, but for application-specific purposes, right? Like Optimism, Flashbots, they're all discovering that they should be thinking about intents, but people still think about transactions. But if you actually want to have decentralized counterparty discovery, you need to be thinking about intents. The other cool thing is that this leads to a very declarative paradigm for application development, where I said in the beginning, currently in transaction-centric designs, you authorize execution traces of how your smart contract is allowed to do compute. In intent-centric design, you don't actually do this. You just say what future state transitions you're fine with. As a result, you don't have to worry about the intermediate steps that get invoked and whether like a proxy contract is broken or not, because you never authorize a proxy contract. I guess as long as that proxy contract returns you the state changes that you are okay with in your intent, this is fine. And this is actually also how sort of the Anoma settlement layer works, is that instead of doing arbitrary compute in the contracts, transactions define what the outcoming, like what the resulting state transitions are going to be, and then all the intents just verify that they're okay with the resulting state changes. For an end user, this has the really nice benefit that it's a black box. Like users author intents, then submit them, then magic happens because they don't care on how these intents get satisfied, and afterwards they just need to verify whether their intent was settled or not. So I'm not going to walk through this entire diagram, but this is sort of a high-level overview of the architecture of Anoma, where on the far left you have counterparty discovery, where users actually write intents, and intents can be either transparent, shielded, or private. If they're shielded, they involve also the generation of a bunch of zero-knowledge proofs. If they're private, they also involve zero-knowledge proofs and fully homomorphic encryption. Honestly, FHE is like at least 5 years out. That's still very exploratory research. Then users sign these intents, they submit them to, their client submits them. Now it hits the intent gossip network. And the nice thing is the intent gossip network can span over many different blockchains at the same time, over many different deployment models of Anoma at the same time. So you have one globally connected intent gossip network that can handle the intents for like the Anoma L1 deployment, the Anoma South Korea deployment, or the Anoma L2 deployment on Ethereum. And because intents can just specify in which security model they want to be settled. Solvers look at a number of intents, maybe they take 15, combine them into a transaction. They submit them to a transaction mempool, but first they encrypt all transactions. So in Anoma, transactions are encrypted against a public key run by the validator set. This uses a protocol called Fairview, which is a distributed key generation protocol. High level, this solves MEV. All transactions are encrypted. Validators only order and propose encrypted transactions. So in block N, you fix the ordering of a list of encrypted byte strings. And in block N+1, the validator set jointly decrypts all the encrypted transactions and then executes them. But at that point, they can't sandwich, front run, or back run you anymore because the ordering has already been established. Yeah, now you have a finalized block, and then you go into the execution verification environment, which is a unified execution environment that you can be deployed to many different sort of settlement layers. This also allows you to, one of the very nice things about the unified execution environment is that it handles transparent, shielded, and private state at the same time. As in, you can write applications that are partially transparent and partially private, because this will honestly depend on the specific applications, on how much privacy or at what level do they need privacy. And then in the end, users just can verify the settlement of an intent. How many? Time is fine. Right, homogeneous architecture, heterogeneous security. So, one of the important things to sort of realize is that protocols can easily be benevolent monopolies. Like, we all benefit from agreeing on TCP/IP as a standard. No one actually makes any money on this, but it's just nice that we can use the same protocols to talk to all the servers in the world. This is also why our phones are pretty cool, because we sort of globally agreed on a cellular backbone standard, and my phone that I bought in Europe works in Asia, as well as in North America, as well as in South America, as well as in Africa, right? Like, my phone can use the same protocols to roam in different security models. And the big thing to realize is like that the losses of protocol standardization are like very minimal. Like, sure, we could build a slightly better version of TCP/IP, but we would lose much more by the fragmentation of having a ton of different protocols than we would by sort of the tiny losses that we take because maybe TCP/IP isn't exactly optimal. The very important thing, though, is that security domains should not be monopolies, because security domains are, for example, a country is a security domain, right? Like, a validator set is a security domain. Like Ethereum is one specific security domain, and it can charge rent, it can steal funds, it can collapse, right? Like different security domains have different security properties, and they can fail independently of each other. And as users, we want to be very capable of not, like this is not about telling people what kind of security they should be using. It's more that people should have a choice. As in, maybe to my parents, it's preferable that all their digital assets are secured by the 200 people in their village, because this is sort of their local trust zone. This is the people they trust. But maybe someone that lives in Argentina really wants to have their assets in the global Ethereum security model, because they don't trust their local government, but they trust the global Ethereum model. So yeah, we should be separating protocols and architectures from the underlying security models. Currently, we tend to very much tie them together. So this leads to the nice fact that you can deploy Anoma as an architecture in many different ways. You can deploy this as an L1, as a sovereign chain. This is what we are currently doing as a first step. You can deploy them as community-operated chains where, let's say, the World of Warcraft community wants to have a financial settlement backbone. They can take this architecture and run it themselves. The city of Seoul can do this to run the financial system in Seoul. You can also deploy this as an L1.5 if you just want to decentralize a specific dApp construction. So for example, you could have a specific deployment for, let's say, OpenSea. Or you can deploy this as a generalized L2 where you build the dApps, where you use the distributed decentralized counterparty discovery and solving component of Anoma while keeping all the settlement to Ethereum. Yep, so in the first case, you just use the intent Gauss subnetwork only and sequence and settle elsewhere. The second model is you decentralize the solvers, i.e. you decentralize the rollup sequencers or the provers or the OpenSea servers, but the settlement still happens on your preferred security model, which I think for most people in this room, including me at the moment, is probably Ethereum. Or you can also use this to decentralize specific applications, or you can deploy Anoma as a fractal instance with local settlement guarantees. So how do dApps on Anoma actually look like? Well, they have intent formats. This is something people need to agree on. They have solver algorithms, which don't have to be optimal. They just have, most likely applications on Anoma should just provide a standard solver implementation so that at least there's some baseline solvers available. But there's a huge incentive for people to build their own solvers that are, because you're competing effectively. You're trying to, the people that can most efficiently solve can settle most intents, and they can gather the fees from them. And then you also have validity predicates, which are settlement invariants for users or applications. For example, if you're transacting with Bitcoin on Anoma, the settlement invariant for Bitcoin is that Anoma cannot create or destroy Bitcoin. So applications as well as users can have settlement invariants that need to be enforced. This kind of vertically integrated architecture means that you get end-to-end security, liveness, and privacy guarantees. And importantly, that like our phones, applications are portable across security domains, as in your application, your wallet can start roaming between different blockchains as long as we all agree on similar kind of protocols. So what can you build with Anoma? Well, you can build, and this sort of goes back to the earliest thing, which I said when we went from Bitcoin to Ethereum and now to sort of this Anoma architecture, that we didn't think of all the applications that you could be built using this kind of architecture when we built Ethereum. And I think there's a number of existing dApps that I can see using this kind of stuff. But I think there's also going to be a large number of applications that haven't been explored yet, because we're just starting to sort of think about what this generalized architecture means. So existing dApps you can build with full stack decentralization are things like fungible token swaps, like 0x CowSwap, non-fungible marketplaces, Wyvern, Seaport, OpenSea. You can build very capital efficient AMMs because you don't need capital locking. And you can decentralize the rollups using Anoma. You can do public goods funding. So Gitcoin without the semi-trusted multisig, where everyone's commitments to fund a certain project are just intents. And once you reach a threshold, a solver can figure out what is the best combination of these intents, which project should receive the right amount of funding. But there's also a ton of novel dApps that I can already think about that require more than simple programmable settlement. Things like private DAOs, private auctions. So Anoma also comes due to the fact that we have a threshold decryption system that prevents front running. We also get effectively a programmable threshold decryption where applications can say, here's a batch, all transactions for this specific application are encrypted, let's say for the duration of this batch, let's say 10 blocks. And this is what you use in order to build like second price auctions that aren't front runnable, because everyone in the auction submits their bits. They're encrypted for the batch duration or for the auction duration. They can be defined by the application. Afterwards, the validator set decrypts all bits at the same time, and then the application just needs to verify what is actually the winning bit, but no one can inject new bits or remove old bits from it. Yes, you can build private games. I think the thing that I'm most excited about is multi-party, multivariate private bartering. It's the idea that you can, I can say that I want to trade some Bitcoin against some CryptoKitties. Someone else wants to trade CryptoKitties against train tickets in Seoul, and a third person wants to trade like train tickets, if the weather is nice, against Bitcoin. As long as the weather is nice, all these three things are combinable and settleable, and this like scales to end-party bartering, as in you can have 1,000 individual intents that are all settleable together. Which means as a user, I don't have to worry about like figuring out the right route for my asset. I just say what I have and what I want, and as long as there's some sort of path, intents can represent this. And you can build on-demand runtime rollups, because what is a rollup? Essentially, a rollup is a computational compression. Once you have an intent that goes from A to B, and another intent that goes from B to C, and a third intent that goes from C to D, you can just collapse them to one intent from A to D. And this is so high level what rollups do. Yeah, so Anoma is built by Heliax. These are my two co-founders. So it's ours here as well as in the room. The team is much larger than this, so we couldn't build this with the three of us. So check out the team. Yeah, and this is Anoma for you. It's a unified architecture for full stack decentralization.